Okay, so it really is a pleasure today to have Dr. Pierre St-Laurent, who is at the Virginia Institute of Marine Science, as our seminar speaker. Pierre's, as you might have gathered from the conversation going on just before we started this, Pierre is
Alexa,
from Canada.
stop.
I'm sorry, who is that? So he's from Canada, and did his PhD work at the University of Quebec, after which he came to actually Old Dominion University to work with Mike Denneman and John Klink, and to some extent with me as well. But then he went on to the Virginia Institute of Marine Science, where he's been working with Marjorie Friedrichs and other people at VIMS. And he has done a number of really interesting projects related to the Chesapeake Bay. We'll hear about some of them today, but before I introduce those, I should say that Pierre is part of a NOAA MIRHAB, the Monitoring Environmental Responses to Harmful Algal Bloom program that's just really getting started for the lower part of the Chesapeake Bay. But today what he's going to talk about is coastal acidification, tropical cyclones, and alkalinity enhancement, a look at select Chesapeake Bay research projects. So Pierre, please go ahead. Thank you.
Thank you, Arlene. I gather that you can see my slides.
Yep, looks good.
All right. As Eileen said, I will be talking about a couple of research projects in the Chesapeake Bay, but I figured this was not a bad audience to talk before then about an atlas that I created recently for the Chesapeake Bay. And you might ask yourself, do we really need yet another data set about the Chesapeake Bay? Aren't we flooded with information about the bay? And to some extent, I will agree. Here, I'm just showing some of the most important data sets that are available online publicly. And it's a treasure trove of information about the bay, no question. And yet, if you look at the questions I selected on the left, none of the data sets I showed in the previous slides actually answer these basic questions. Things like which month of the year has the highest wind waves in the bay, where and when is water chemistry appropriate for shell calcification in the bay. These are fundamental questions, and it's actually hard to get answers just from the reference I listed in the previous slide. So that prompted me to try to do something about it, try to fill in the gap with what I had in hand, which in my case was 4 decades worth of information about the atmosphere, the waves, and then those correspond to the input to a Chesapeake Bay model that I've been using for a few years. And then I had 4 decades of model outputs, so the hydrodynamics, carbonate chemistry, nitrogen and carbon cycles. And so all of this information that I happen to have in my hands for 1985 to year 2023, it was 2.5 terabytes. And I know from experience that there's nobody in the world who would be interested in downloading that. So I thought, could there be a way to distill in this information a little bit further and get a product, a data set that would be interesting to a wide audience of Chesapeake Bay students, researchers. So one way to summarize this information, I decided to focus on the surface and the bottom of the bay only. I decided to only focus on a monthly climatology, so the 12 months of the year with January corresponding to an average of all the January between 85 and 2023. And then I condensed all the information into a common grid of latitude, longitude, with a resolution of approximately 600 meters by 600. So that was enough to give you a sense of an atlas, and the result is only 100 megabytes in size, something that you and I can download in 2 or 3 seconds on a Wi-Fi connection. On the left, I'm listing all the variables included inside the atlas. It's a total of 27 variables. There's a little bit of everything: hydrodynamics, biogeochemistry, and also carbonate chemistry. And I decided to make this available in 3 formats. The first one is just a regular PDF. It has a very comprehensive evaluation of the model results. And then it has 45 pages of visualizations that you can quickly consult if you are interested. The second way in which I'm providing the information is through web maps. And finally, for the power users, I created these georeference rasterized layers that you can use in any popular product. Here I'm giving an example of those web maps. They are available at the link at the bottom right. And we've seen these kind of maps throughout the internet. They are very convenient to use on a smartphone. You can zoom and scroll as you wish. And as usual, there's a number of layers, so you can switch between different variables, different time of the year. It's probably the quickest and most convenient way to look at the atlas. Then for the power users, here's an example where you would open the rasterized layers inside the QGIS. And it's all georeferenced, so you can immediately add your favorite layer on top of it. Here, in this case, I added the segments from the TMDL on top of bottom alkalinity from the atlas. This is another example. It's a Python script, and all the script that I'm showing right now are available on the website. So there are good examples on how to exploit the atlas in an efficient way. In this case, I'm focusing on calcification of eastern oyster, which is a function of the calcite saturation state. That's the horizontal axis in the figure on the left. And essentially, once you are in the right portion of the diagram, you're calcifying, creating oyster shell. Once you are on the left of this threshold, you are dissolving your oyster shell. So once you have a function like this and you have the atlas, which includes the calcite saturation state, you can translate the function into actual heat maps and obtain an idea of where calcification is likely to be taking place in the Chesapeake Bay. One last example of using the atlas. This is an example in R. We had a student at VIMS who was working on sandbar shark in the bay. And he had all these lab experiments where he essentially quantified the preference of sandbar shark in terms of salinity, oxygen, and temperature. So those are the GAM functions you're seeing on the left. Once you have the atlas, you can take these ugly gray functions and translate them into a vivid color map for habitat suitability of sandbar shark directly. So it's an interesting tool, and I hope you can take a look at some point. So moving on to the research project I wanted to talk about. The first one is about coastal acidification in the York and the Rappahannock. So that was a NOAA-funded project that ended very recently. The goal was to look at the vulnerability of the industry to ocean acidification, OA, and a few co-stressors. It was a large project. It had a social science component. It had some observationalists, and then we were in charge of the modeling component of the project. My main contribution is I took my existing Chesapeake Bay-wide model that has a 600-meter resolution, and I created this high-resolution nest over the York and the Rappahannock. And I use a 5-fold refinement of the grid, so that gives me resolution of 120 meters throughout this little nest. To give you some idea, in Virginia, a typical oyster lease is 250 acres. So that will be resolved with 70 grid cells with this resolution. The figure on the left is showing a static image of bottom alkalinity, but I can show you what it looks like in action. So the video that's playing on the right, it's bottom oxygen from this high resolution nest at the mouth of the York and the Rappahannock. Obviously, it's playing over a couple of tidal cycles, which is the pulsation that you're seeing in the video. And it gives you an idea that 120 meter is sufficient to see a lot of the spatial and temporal variability. As I said, this is embedded into RUMS. RUMS doesn't do oysters by default. This is something that we needed to add. What I did is I went to my colleague, Mark Brush, and borrowed his eco-oyster module. I converted equations in Fortran and then made it a RUMS module. The components of eco-oyster, you have the shell weight for the oysters and then the tissue weights. Those are the two state variables. Ocean acidification comes into the calcite saturation state that determine whether you're calcifying or dissoluting the shells at a certain grid point at a certain time. And then for tissue weight, you have the usual suspects. Filtration is your source term, and then you have the losses term, respiration, spawning, etc. Next, we were interested in the vulnerability, and we quantified this by contrasting the oyster growth in the recent past and compared this with the oyster growth in the year 2060. So the experimental plan, there were 5 model experiments total, the first one being just a control for the recent past, and then increase atmospheric CO2, increase atmospheric temperature. We had a scenario where the nutrient loads would satisfy the TMDL from the Chesapeake Bay program. And then finally, the last experiment will combine all of these future conditions into one single experiment. The reason we had more than just 2 experiments is sometimes it's very useful to be able to say whether this future change was linked to the increased atmospheric CO2 or the increase in temperature. All of the results I'm showing assume that the oysters are positioned at the bottom, meaning that they would be located in cages at the bottom, and that's the standard aquaculture practice in Virginia. The person in charge of analyzing the results was a master's student, Catherine, and she's now at UVA working with Scott Downey. So here I'll be summarizing the main outcome from Catherine's study. The table at the top is summarizing the change in the environmental conditions and in the oyster conditions between the recent past and the 2060s. And I'm only showing spatially average and seasonally average values. What were the highlights of those results is that we saw a large reduction in the calcite saturation state. To give you an idea, if you average over the York, a typical calcite saturation state would be on the order of 2, 2.5, and we saw a decrease of minus 0.9 simply from increasing the atmospheric CO2. So that's a substantial decrease that would immediately impact shell dissolution in specific months of the year. So we obviously saw a reduction in the shell weight of the oysters. What came out as a surprise is the magnitude of that reduction. It was a 68% drop in the weight of the shell. So that was a surprise. The other surprise that came out is that tissue weight was also seriously impacted in the climate simulation. It reduced by 59%, mostly because of the impact of atmospheric warming. So those values were more dramatic than we had expected, and it forced us to dig deeper a little bit into eco-oyster and figure out why were these changes so important. That's what I'm doing in this slide. In the left part, I'm focusing on the decrease in shell weight of 68%. If you look back at the equation, what controls the shell weight is a lot more than just ocean acidification. It's actually a direct function of the tissue weight of the oysters. So it turned out that the primary reason for the decrease in shell weight was that the tissue weight had been decreasing by a similar amount. acidification basically played a secondary contribution to the reduction in shell weight. So that leaves us to understand why is the tissue weight changing so much in these future climate scenarios. So the figure on the right is showing you what I would describe as the guts of eco-oyster. In the blue, on the left-hand side of the figure, you have the temperature dependence of the filtration for the oysters. And then on the right in red, you have the temperature dependence of the main sink term, the main respiration term for the oyster. What we're seeing is that respiration is assumed to follow an exponential increase with temperature, rising temperature. But for filtration, the function was taken from Carl Circo's study in 2007, where they assumed that once you're past 20 degrees C, the filtration starts to gradually drop, eventually reach a plateau around 27 degrees C, and then filtration is assumed to start to collapse at higher temperature. So what happened in the case of Catherine's study is that once we went into climate change and started looking in the year 2060, we are basically spending more and more time on the rightmost part of that figure where respiration outweighs the filtration. And that's the main reason why we saw such a dramatic reduction in tissue weight in the future climate experiment. Interestingly, if you go back in the literature that Carl Circo used to justify this curve, there's actually not that much of a consensus on what the function should look like. There is tremendous amount of variations in experimental design. Some oysters show adaptations in certain areas where they are not that sensitive to increased water temperature. And in some cases, lab experiments don't even go that far in terms of temperature. And so there's unfortunately quite a bit of uncertainty in what this blue function should have been. And that is possibly leading me to say that these results might be overly pessimistic as to how the oysters will be behaving in 2060. Despite this, Catherine was able to make a few recommendations based on her study. And the first one would be that the oyster aquaculture in Virginia would benefit from moving from bottom cages to floating cages. The reason for this is that the calcite saturation tend to be higher at the surface than at the bottom. And so if you're moving suddenly from bottom to surface, you're giving yourself that much more slack to handle a decrease in carbonate calcium when the atmospheric concentrations are increasing over time. The other recommendation that Catherine made was, if it is true that the filtration rates plateau and then start to decrease with high temperature, there will be a benefit from deploying the oysters at an earlier portion of the year. Typically, it's done in the spring and continues into the summer, but making just a shift of a few weeks could make a huge difference in those higher temperatures. So you can check out the manuscript that Catherine has submitted. The next project I wanted to talk about briefly is this retrospective analysis of Hurricane Irene in 2011.
There?
Yes. Did I hear something?
I think it's okay. Go ahead.
Okay. So Hurricane Irene hit the Chesapeake Bay in August 2011. Hundreds of thousands of people were evacuated, $13 billion of damage in the country. It was sufficiently bad that the name Irene was permanently retired and eventually replaced by Irma. My experience of Irene was not that exciting. At the time, I was living on the shore of the Lafayette River at this large apartment building called the Lafayette Towers. And one day I was coming back from CCPO and saw the little sticky note on my door telling me that I was among the fortunate ones who were into a mandatory evacuation zone, in which case I simply walked back to the campus and spent 2 nights at the Spring Hill Suites next to Hampton. by the time I left the hotel, Irene was over, and there was not that much to see. So we can look back at the timeline of the storm and get an idea of what exactly happened while I was asleep at the hotel. These two figures are showing the sea surface height detided as a heat map, and then obviously the quivers are the wind at the same moment. So I'm contrasting two different times. The first one is about 8 p.m. on August 27. At that time, the eye is roughly about over North Carolina, and the winds are such that this is when you're actually getting the maximum storm surge over the Hamptons Roads area and at Sewell's Point. So that was about at 8 p.m. local time on August 27. Unfortunately, this peak storm surge of 1.36 meters above the astronomical tide happened to be coinciding with also the peak tide, which was at midnight and 30 UTC. And that by itself added an extra 0.4 meter on top of the storm surge. And eventually, 9 hours later, the storm was continuing on its northeastern path, and the winds had shifted in such a way that gradually the storm surge could recede and the water was getting flushed out of the Chesapeake Bay. One thing I was interested in this study was how typical was Irene compared to other tropical storms that have affected the Chesapeake Bay. So what I did is I dug into the HERDAT data set so that it's a retrospective analysis that goes back to 1851. And what you're able to do is to create a subset of all the tropical cyclones. And I specifically requested only those that went over this blue rectangle, which I call the Chesapeake region. So the answer is that there has been 121 tropical cyclones that passed over this little blue rectangle region since 1851, so about one every 1.4 years. It's very likely that HERDAT undercounts the number of tropical cyclones, obviously, because 1851, there wasn't that much coverage. But nevertheless, it gives you an order of magnitude for how frequent these events are directly affecting us. Of those 121 tropical cyclones, about 2/3 had reached the hurricane level at some point in their lifetime. The other thing I was curious was, what's their typical trajectory? So those are the spaghettis that I'm showing in light gray. It turns out that there's an even split between the number of tropical cyclones that reached the Chesapeake Bay from land, so eventually going through the Gulf of Mexico and then over Georgia, South Carolina, and eventually reaching us. And then the other half of those tropical cyclones tend to follow the typical path over the Atlantic and eventually hit North Carolina and Virginia, just like Irene did in 2011. So that's for the winds. We can also look at the precipitation. The figure on the left here is time, basically the rain accumulated over a number of days surrounding the passage of Irene. So those are centimeters of rain. And then the blue outline is the extent of the Chesapeake Bay watershed. I was interested to see exactly how much of the rain associated with the storm actually hit the watershed, because that's what matters if you're focusing on water quality inside the bay. And it's interesting to see that to a large extent, the rain hit south of the watershed and also northeast of the watershed, and not so much the watershed itself. If you were to compute from ERA5, all the rain that fell because of the storm over the latitudinal range of the watershed, you will see that the vast majority missed the watershed. It's only 26% of the rain over that range that was falling over the watershed. So that leads me to say that to a large extent, Irene could have been a lot worse in terms of precipitation and river discharge. I can contrast this with another storm that hit the Chesapeake Bay a month later. This is Tropical Storm Lee. And you can see that in that case, the precipitation was right over the northern half of the watershed, which eventually led to the highest discharge in record for the Susquehanna River. So not particularly impressive in terms of precipitation, Hurricane Irene. This one I will skip. It's just more context. So in terms of research studies, there's lots of papers that were written about the flooding during the time of Irene, but there's not that much known about the water quality impacts of storms like Irene inside the Chesapeake Bay. If you look back at the data collection, like the Bay Monitoring Program, they just don't have the frequency to have a good comparison of a before and after the storm. The program it's not designed for sampling these kind of things. So what I did in my case is I'm part of the ICOM project funded by DOE, and they've been focusing on Hurricane Irene for their analysis of the atmosphere. Essentially, what they've been doing is initializing their atmospheric model on August 26, a few days before the storm, based on a reanalysis. And then they conduct their atmospheric model forward in time. And they do this repeatedly with small variations in the parameters of their atmospheric model. So what you get after doing this is an ensemble of high resolution atmospheric fields that are slightly different than the real Irene that we experienced in 2011. I'm using this data set, this ensemble of 50 Irene-like storms, in order to see to what extent water quality impacts inside the Chesapeake Bay change as a function of small change in the characteristics of the storms. So you see on the right, you see that some of these ensemble members arrived a little earlier, a little later. Some of them were more intense, less intense, more or less rain. And I'm just examining to what extent these small changes are having an impact on water quality in the bay during the storm. Some of these results were more or less expected. Some more or less were quite obvious in hindsight. One thing we found out is that some characteristic of the tropical storms were interrelated. The precipitation over the watershed tend to increase if the storm was moving slower on its track. And also the precipitation would increase if it was closer to the bay. That was interesting by itself because according to the literature, there's a trend where tropical cyclones are actually having their translation speed slightly slower as the Earth is warming, which by itself would suggest more precipitation over the watershed for the same type of tropical cyclone. Other things we noticed that were relatively obvious, the turbidity, the vertical mixing inside the Chesapeake Bay was directly following the intensity of each of the tropical storm inside the ensemble. We saw that vertical diffusivity was inversely related to how much rain fell over the watershed, which we interpret simply as all this buoyancy coming from the rivers being a sink of turbulent energy. Perhaps less obvious was this last bullet point here. If you're concerned about flooding in your house following a tropical storm, you might expect that the stronger the storm, the more flooding you can expect. And it turns out that it's only weakly related once you look at the statistical relationship. The best predictor for the magnitude of the flooding in the bay turned out to be the wind across the mouth of the bay. And that's very likely to change depending on what's the actual track of the storm, regardless of its intensity. We also had some results that were surprising, not obvious at all. We saw that how much rain you had over the watershed, the more rain over the watershed tend to reduce the turbidity rather than enhancing it. My first expectation is the more rain over the watershed, the more suspended solids you're bringing from land, and that will increase turbidity. And that's not what we saw. We actually saw that the water was having this extra buoyancy, was impacting vertical mixing and sediment resuspension, and that was the main way in which turbidity was affected by the rain and the river discharge. Another surprising result was that bottom oxygen was completely wiped out, bottom hypoxia, was wiped out during Irene, even though it took place in August, the month where hypoxia is maximum normally. It's not always happening that way. You might think that all storms have strong winds, they all affect hypoxia in the same way. Really not. If you look at Tropical Storm Lee that came approximately a month after Irene, it had weaker winds and a tremendous amount of precipitation. And so it did the exact opposite. It brought lots of organic matter in the bay, lots of nutrients. And this time the storm actually made hypoxia go up. So overall, this analysis so far, what it is showing is basically reminding us that Irene was mostly a windstorms. And so the wind impacts over water quality are far dominating the impact of rain over the watershed and river discharge. And what we're looking at this moment in terms of ongoing work is the contribution of the storm overall on the carbon budget of the bay and how much outgassing was happening during the storm and after the storm. The last project I wanted to talk about quickly is one that was recently funded. It's about alkalinity enhancement. And it was funded by ARPA-E, which began in 2016. So it's a fairly young funding agency if you compare it to NASA or NSF. So for those who are not familiar, its goal is to promote and fund research and the development of technologies. And one way to put it slightly different is that what they're trying to do is to provide initial funding to push ideas out of the labs, out of the universities, and hopefully come up with a successful marketing plan. So in our case, this is how it works. We are specifically playing in the field of emission reduction, carbon credits, which required some form of certification to verify that carbon was actually sequestered. So sometimes this is described as the MRV acronym, Measure, Report, Verify. So our project has a number of components. The first one is a bunch of lab experiments where they are testing different alkaline materials, trying to establish their pros and cons in the context of microcosm and mesocosm experiments. Then more closer to me, her role is to develop a module, so a piece of software that will allow existing biogeochemical codes to suddenly simulate secondary precipitation of alkalinity. And that is actually our product, and it is targeting any RUMS modelers that is involved in OAE. And so all these modelers that would be interested in using our module, that's our market, if you will. And ultimately, the goal is to evaluate the efficiency and the scalability of doing OAE in different regions of the world. Just a quick background about ocean alkalinity and enhancement. I guess the simplest way to describe it is you're dissolving an alkaline material at the surface of the water column that will lower the partial pressure of CO2 and will generate a flux of carbon from the atmosphere to the ocean. Ideally, you want this alkalinity enhancement to be as efficient as possible, meaning you get as much bang for your buck. The way you would calculate this is by this ratio here. It's how many moles of carbon is sequestered per mole of alkalinity that you have injected at the surface of the water. So it can be anywhere between 0 and 1. And there has been a number of studies that calculated this efficiency at different locations throughout the world's ocean. The figure on the right is an example of that. It's Zhu et al. 2024. They literally dumped alkalinity at the surface of their ocean model to try to map out which locations are actually a good targets for OAE in the global ocean. The one thing that came out from these maps is that vertical mixing and stratification appears to be the thing that we should all keep in mind. Essentially, if you release your alkalinity in a region of strong mixing, most of it will be dispersed over the water column and will be basically not in contact with the atmosphere anymore and will not be doing what you are expecting, which is contributing to a flux of carbon. And then obviously stratified regions appear to be associated with higher efficiency up to 0.9, simply because TA stays longer in the surface mixed layer. This efficiency can actually be negative if you add too much alkalinity, meaning if you let the aragonite saturation state reach values on the order of 7, you can get into a situation where you will have runaway precipitation. What used to be dissolved will start to precipitate, and eventually you will find yourself in a situation where TA will be lower than if you had done nothing. If you reach that point, then your efficiency is negative and you're actively doing the opposite of what you wanted in the first place. So precipitation is a challenge that you see often in the literature. So as I was saying earlier, it's a collaborative project that is attempting to examine these questions into 3 regions of the US: Gulf of Alaska, Salish Sea, and Chesapeake Bay. The reason these 3 were selected is because they happen to correspond to established RUMS biogeochemical model that have been there for a long time. What's good about these 3 regions, I would argue, is that they span a spectrum of alkalinity values. It's anywhere between 2100 in this mostly oceanic environment down to 1400 and then 1000 in the Chesapeake Bay, or sometimes even lower inside some tributaries. So we're really covering a spectrum of background alkalinity conditions. And we expect just from the physical oceanography of these 3 regions that what is the right time to be releasing alkalinity and get the most efficient result will be very different across these 3 regions. You remember from the previous slide that a lot of the experiments so far have been conducted in the perspective of releasing alkalinity in the open ocean. And so you might ask yourself, why would you look at these questions in the context of a small estuaries like the Chesapeake Bay? One answer is that it is tremendously cheaper and more convenient to release alkalinity from existing coastal infrastructure if you get a similar scalable result. And that's one question that we have to figure out in this project is, can it be done in an efficient way in a small body of water like the Chesapeake Bay? And here I'm just showing a preliminary experiment. In this case, it's a simulation that I did where alkalinity is being released in the northern part of the bay. So it's on top of station CB 2.2. And essentially what I'm doing is I'm injecting it at the surface for a total amount of about 40 millions of moles. And I'm doing it over a period of 20 days. The reason why you would do this is it allows you to ramp up and down the flux of alkalinity at the surface in such a way that the tides and the winds are given enough time to dissolve that alkalinity and reduce concentration below the threshold that you would expect for precipitation to take place. So that's why you're basically distributing the flux and ramping it on and off over time. And then you need some metric to know how much carbon was actually sequestered by your addition of alkalinity. The way we do this is we conduct 2 actual model simulation with and without the OAE. And then we simply integrate over the vertical the difference between the two DIC profile. And then you can also integrate laterally to get the overall amount of carbon that was sequestered and compare it to the amount of alkalinity that you've rejected. So I'm going to play just a very quick video. The shading, that's the carbon sequestered in millimoles of carbon per square meter. And in the time series on the right, that's integrated over the full model domain. And the idea is to compare the amount of alkalinity that was added and to see how much carbon was sequestered at the same time. So, all right. So once again, the injection of alkalinity lasts over a period of 20 days, after which you see the blue time series times reaches a plateau. That means we've stopped increasing alkalinity. And then at that point, it's simply tides and winds that are dispersing the alkalinity throughout the Chesapeake Bay model, vertically and horizontally. And you can see that even within a very short period of time, something like a month or two, the orange curve is already something like 0.8, 0.9 of the blue curve, meaning that you reach an efficiency of 0.8 or 0.9, which is comparable to perhaps the best results that Zhu et al. 2024 was showing for the open ocean. So what this suggests is that basically that we're in a situation where perhaps it is feasible and efficient to be doing ocean alkalinity experiment in a system like the Chesapeake Bay. The open question that needs to be figured out through the course of the project is, what's the long-term fate of all that DIC that was sequestered? To what extent can precipitation can complicate these high efficiency that we saw? And how scalable is this approach? Can we really do it for long periods of time and have a satisfying amount of carbon captured from the atmosphere? So those are the things that we will be playing with over the upcoming years. So thank you for your time. I appreciate it, the opportunity. And